So this is an advanced higher chemistry lesson, and again this is part of the physical chemistry section in Unit 1, and this is the second lesson on equilibrium, and we're going to start at looking at equilibrium of water and equilibrium in water. So specifically what we will learn about today is that ionic product of water, and we'll learn a bit more about pH and introduce pOH. So, ionisation of water. This is something that you have known about and looked at probably even before National 5, that water can dissociate into ions. Now previously you may have been introduced to these ions as the hydrogen ion H+, and the hydroxide ion OH-. However, that's not the full story. And actually, an H+ ion is technically a proton on its own, which would not be stable to exist on its own, and it has to actually attach onto something else in order to be stabilized. So what ends up happening is two water molecules form an equilibrium where we end up with an H3O+ and an OH-. Now what you can imagine is happening is that we know that two water molecules, a hydrogen bond would form between the hydrogen of one water and the oxygen of another. What's happening in this ionization process is that the hydrogen of one water molecule, that is forming a hydrogen bond to the oxygen of another water molecule, ends up completely jumping ship and moves over to that second water molecule, leaving a hydroxide ion and forming an H3O+ ion. So you can see how these happen all the time, and those protons essentially are jumping between water molecules, and it's reversible. So once you've got an H3O+, one of those hydrogens doesn't have to be the original hydrogen, but one of those three hydrogens can jump back onto a hydroxide ion in order to turn it back into two water molecules. Now the OH- ion is still called a hydroxide ion, however the H3O+ is called the hydronium ion. So hydro for water, and in a similar way to ammonia becomes ammonium, water, hydro becomes hydronium, which indicates it's a positive ion. Hydronium ion and a hydroxide ion. In the equations that you'll see, we are going to use H3O+ to represent the hydronium ion. However, you may sometimes see in textbooks, online, and possibly even in your exam, sometimes hydronium, even at advanced higher, gets shortened simply to H+. But you should keep it in mind that an H+, if it is in a solution, is always going to be a hydronium ion and not an H+ on its own. So keep that in mind, and if you're wanting to be exact and precise, make sure you always use H3O+, hydronium ion, and not just H+. So hydronium and hydroxide ions. The hydronium ion is the ion responsible for making solutions acidic. The hydroxide ion is the ion that is responsible for making solutions alkali. Water has hydronium ions and it has hydroxide ions. So water, although it is neutral, it's actually acidic and alkali in equal amounts. And a chemical like water that can act like an acid and can act like an alkali has a special word used to describe it, and that word is amphoteric. So amphoteric describes a chemical that can behave as both an acid and a base or an alkali. Another example is aluminium hydroxide. That's another amphoteric compound. But water can behave as an acid and an alkali. Now we're going to look at the equilibrium of water because obviously in the previous lesson we learned how to set up equilibrium expressions and work out equilibrium constants. So we're going to do that. We're going to write an equilibrium expression for the dissociation or the ionization of water. And because water is so ubiquitous, is so prevalent in chemistry, we actually give it a special equilibrium constant value of Kw. And we could see it would be H3O plus multiplied by OH minus divided by H2O squared. But at this point, I'm hoping that some of you, if not all of you watching this video, would realize that there's something wrong with that equilibrium expression. And the thing that's wrong is the fact that water is a pure liquid, has the state symbol L. And as such, the concentration of water gets simplified to 1. And if we end up simplifying it to 1, we can simplify the whole expression Kw to H3O plus hydronium multiplied by OH minus hydroxide. And so it's been simplified to the product of two ions. And that's why Kw is often not called the equilibrium constant for water. It's sometimes called the ionic product of water because it is the product of the two ions that form in water. But it can also be called the dissociation constant of water. And it's Kw. Because Kw is an equilibrium constant, it is subject to change depending on the temperature. However, at 25 degrees centigrade, which is the equivalent of 298 Kelvin, Kw has an exact value, and that value is 1 times 10 to the minus 14. And the fact that it's 10 to the minus 14 might be the number 14 in relation to chemistry might be ringing a bell in some people's heads, and with good reason. And you'll see if you have, think about the number 14, what you know in chemistry, do with the number 14, and let's see if you can work out where we're going. It's related to the pH scale. The pH scale goes from 0 to 14. The reason it goes from 0 to 14 is because the ionic product of water has this value of 10 to the minus 14. pH, you probably did know, was related in some way to the concentration of H plus ions. We now know that H plus ions are more correctly called hydronium ions, H3O plus ions, and pH is equal to minus the value of the log, or this is the log to the base 10, of the concentration of hydronium ions. So if you're doing this in your calculator, you would press the negative symbol, you would press the log number, and then you would type in the concentration of H3O plus to give you your value. If you wanted to try and work out the concentration of hydronium from a pH value, the reverse is to do 10 to the negative power of the pH, tell you the concentration of H3O plus. So for the future lessons relating to water, you are going to have to get familiar with logs, which you should have done in National 5 or higher maths. Now in pure water, we're going to look at pH and we're going to look at Kw. So in pure water, that means it's not acidic, it's not alkaline. In pure water, we know that the total concentration of H3O plus is going to be exactly the same as the concentration of OH minus. Because for every 2 water molecules, we get 1 hydronium and we get 1 hydroxide. So they have to be constant and equal to one another. So Kw, the ionic product, is equal to the concentration of H3O plus multiplied by the concentration of OH minus. We know that the ionic product of water at 298 degrees Kelvin or 25 degrees C equals 10 to the power of minus 14. You could also write that as 1 times 10 to the power of minus 14. But again, remember, we know that the concentration of H3O plus and the concentration of OH minus are the same as one another. So what we're going to do is, in the equation, we're going to replace OH minus just with another H3O plus. We're going to substitute. And that means that 10 to the minus 14 is now equal to the concentration of hydronium squared. And what we need to do now, we want to try and find out what the concentration of H3O plus is. So we're going to take the square root of each side. Now, whenever you take the square root of something that's got a power, that means you divide it by 2. So 10 to the minus 14 becomes 10 to the minus 7. And we now know a concentration of H3O plus, which means that we can calculate the pH. And pH is minus the log of the concentration of H3O plus. That is minus the log of 10 to the minus 7, which is 7. So the pH, which is related to the concentration of hydronium ions, is 7 in pure water. There's an alternative way of looking at the ions in water rather than focusing on the H3O plus or the H plus concentration. You can look at the hydroxide concentration. And pOH, it's not used as widely, but it is just as valid to use. And pOH, the same relationship, it's the minus log of the concentration of hydroxide. And if we want to find out what the concentration of hydroxide is, it's 10 to the power of minus whatever the pOH is. So in pure water, again, remember, we know that the concentration of H3O plus equals the concentration of OH minus. In our previous calculation on the last slide, we found out that the concentration of H3O plus was 10 to the minus 7. That means that the concentration of hydroxide is also 10 to the minus 7. And so if we calculate our pOH using the equation at the top of this slide, we find out that the pOH is 7. So in pure water, pH is 7, pOH is 7. And we're going to look at how pH and pOH are connected to one another. So in pure water, they're both equal 7. Now, are they always the same value or not? We'll find out. We're going to look at another example. So we're going to look at a solution that is acidic. So we're going to say that it is pH 2. Now, to go from a pH value to a concentration of hydronium ions, we use the equation concentration of hydronium equals pH to the concentration of H3O plus equals 10 to the power of negative whatever the pH is. So that equals 10 to the minus 2. The concentration of hydronium ions in a pH 2 solution is 10 to the minus 2. From the ionic product of water, which is equal to H3O plus OH minus, we know the ionic product of water is 10 to the minus 14. We know that the concentration of H3O plus is 10 to the minus 2. We now want to find out what the concentration of hydroxide is. So what we need to do is divide each side by 10 to the minus 2. And that gives us that the concentration of OH minus is 10 to the minus 12. pOH is equal to minus the log of the concentration of OH minus, which is minus the log of 10 to the minus 12, which equals 12. So you can see that at pH 2, the pH plus the pOH value gave us 14. And in pure water, where the pH is 7 and the pOH is 7, pH plus pOH equals 14. So that is our constant relationship. pH plus pOH equals 14. And that relationship is given to you in your data booklet. But now you can prove it through equations. So what we're going to go through are the types of questions that you might get asked, all the possibilities. So using what we know about how to calculate pH, how to calculate concentration of H3O+, and the same for pOH, using the ionic product of water, Kw, and using pH plus pOH equals 14, all the types of questions you could be asked. You could be asked to calculate the pH or the pOH from the concentration of hydronium ions. You could be asked to calculate the pH or the pOH based on a concentration of hydroxide ions. Or you could be asked to determine the concentration of H3O+ or hydroxide from a solution where you've been told the pH or the pOH value. So on the next slide, I've got 3 examples of questions. What I would like you to do is pause the video and have a go at these 3 questions. And remember, you can use your data booklet to help you. You're obviously allowed access to your calculator. So I'd like you to pause it now, and this is you hopefully having unpaused it. So for question 1, the pH of a solution with a pOH equals 3.5. For this one, it's probably the easiest of the questions up there. Remember, pH plus pOH equals 14. So pH is going to be 14 minus 3.5, which means that pH is 11.5. What is the pH of a solution with a concentration of hydronium ions equal to 6.8 times 10 to the minus 8? Well, there are a couple of ways in which you could do this. You could look at the ionic product of water, and from that calculate the concentration of hydroxide, and from the concentration of hydroxide work out the pOH. And what I did was work out the pH and then use pH plus pOH equals 14. So the pH is going to be minus the log of 6.8 times 10 to the minus 8, which I worked out to be 7.17. And then pOH is going to be 14 minus that value, which was 6.83. For the final question, we've got what is the concentration of hydronium ions for a solution where the pOH is 4.2? Again, there's a couple of ways in which you can do this question. You could turn the pOH value into a concentration of hydroxide and then use the ionic product of water to calculate H3O+. The method I chose was to use pH plus pOH equals 14 and then from the pH work out the H3O+. So pH was going to be 14 minus 4.2, which is 9.8. And then the concentration of H plus or H3O+ ions is 10 to the power of negative pH. So that's 10 to the power of minus 9.8 in this case, which by my calculations worked out to be 1.58 times 10 to the minus 10. So this was our first introduction to equilibrium and how it relates to water, pH and pOH. I will continue looking at water and pH in future lessons. So thank you for watching this, and I will catch you next time.